All right, let's jump right in. Welcome back to this explainer. We're now on episode 9 of our deep dive series on US Patent 1264-142. And today we're setting up the ultimate architectural showdown. We're looking at a wildly fascinating period of ecosystem disruption in cloud computing. Specifically, we're going to examine how software architecture has constantly wrestled with this fundamental relationship between data persistence and computational execution. So we'll be tracking the divergence and the ultimate convergence of NoSQL, serverless infrastructures, and the patented Hierarchical Script-Database, or HSD. So here's our roadmap for today. Number 1, the noun and verb divide. 2, NoSQL rethinking data state. 3, serverless decoupling compute. 4, HSDB, complete convergence. 5, the echoes of mumps. And 6, comparing paradigms. Okay, let's start with section 1, the noun and verb divide. To truly grasp modern database architecture, it's actually super helpful to look at language. Historically, software architectures enforced this rigid, almost impenetrable boundary. On one side, you had your database. That was optimized for data integrity and querying. Those are your nouns. Then, sitting completely separated across a network, you had your general-purpose application logic, which executed the instructions. Those are your verbs. We have to frame this deeply technical comparison as a linguistic problem, really, because separating nouns and verbs means you constantly have to translate between the two. Which brings us to the impedance mismatch. This is the architectural friction and translation overhead caused by that rigid boundary. If you've ever lost hours writing complex mediation layers or wrestling with heavy object relational mappers just to get your app to talk to your database, you know exactly how painful this is. Because the database uses query languages and the application uses programming languages, developers are literally forced to build these bloated, heavy bridges. You end up with massive driver libraries, endless parsing overhead, and totally wasted CPU cycles just to get the nouns and the verbs to talk to each other over a network. Moving right along to section 2, NoSQL, rethinking data state. Back in the late 2000s, the NoSQL movement exploded onto the scene, and they were really trying to relax that exact friction we just talked about. They looked at the rigid, flat tables of traditional relational databases and realized, hey, this isn't mapping well to the complex, tree-structured realities of modern web apps. So NoSQL sought to optimize the nouns. They abandoned those tabular schemas for flexible, semi-structured document formats, stuff like JSON and BSON. By grouping data into self-contained documents, it became incredibly efficient to pull complex object data with very few disk operations. It totally removed the need for those heavily priced schema migrations, letting developers handle massive, rapidly evolving datasets without pulling their hair out every time a business requirement changed. Take MongoDB, for instance. Looking at its topology, we see an architecture that is highly optimized for immediate consistency. But notice the bottleneck here. Every single write operation has to route through that one primary node. MongoDB uses a rich, imperative query language and dynamic B-tree indexes, kind of like a traditional database. It relies on replica sets for failover, so you have one primary node for writes and multiple secondaries for reads. And while that's great for data consistency, it introduces geographical network latency because every write command globally has to travel to that one specific primary server. But then you have CouchDB, which went a totally different route, eventual consistency. CouchDB uses a masterless, peer-to-peer system that writes data incredibly efficiently, but the trade-off is it pushes the indexing latency onto the read path. It operates over a native RESTful HTTP API and uses a multi-version concurrency control system instead of a single primary node. It literally never locks the database during writes, it just appends the data. However, to query it, CouchDB relies on MapReduce views that update lazily. So your writes are lightning fast and highly available, but you might experience a slight delay when reading data as those indexes catch up. It's your classic architectural trade-off. All right, let's pivot to section 3, serverless, decoupling the compute. While NoSQL was busy redesigning the data state, the serverless model took the exact opposite approach for our verbs. They decided to just completely isolate the computation. AWS Lambda is the perfect example of this. It represents the complete decoupling of execution from state, breaking applications down into single-purpose functions governed by a rapid, ephemeral lifecycle. When an event triggers, say an HTTP request, Lambda initiates a container, loads the code, invokes the function, and then shuts it right down. The whole thing is entirely stateless. If you need to remember absolutely anything for the next execution, you have to offload that persistent data to an external database like DynamoDB or S3. And here is the absolute game changer when it comes to the bottom line: 0. You are billed strictly in milliseconds, meaning you pay precisely 0 for idle server capacity. If your code isn't running, you aren't paying a dime. Imagine never having to pay for a server that's just sitting there waiting for traffic at 3 a.m. This function as a service model allows for massive autoscaling, from 0 to thousands of concurrent executions in seconds, making it ridiculously cost-efficient for unpredictable workloads. But to actually pull this off, AWS relies heavily on firecracker micro-VMs to securely isolate those floating computational verbs in highly scalable, stateless environments. See, because AWS is running code from thousands of different customers on the exact same physical hardware, security is absolutely paramount. You can't have one customer's function accidentally peeking into another's memory. Firecracker provides hardware-level workload isolation. It acts as a secure sandbox for each ephemeral function, all while maintaining incredibly fast startup times so users don't experience massive lag. Which brings us to Section 4, HSDB, the complete convergence. So what if we just abandon decoupling altogether? Enter the patented Hierarchical Script-Database, or HSDB. If NoSQL decoupled the storage engine and Serverless fully decoupled the compute, HSDB asks a wild question. What if the code and the data were the exact same thing? Instead of a network separation, HSDB uses this fractal math equation to treat code and data as structurally identical, or isomorphic. Now, I know fractal math sounds a bit intense, but think of it like this. Instead of normal cyclic loops you'd see in standard programming, it uses a non-halting mathematical loop that allows the database to naturally and infinitely stack input and output data. It creates one single infinite coordinate system where execution and storage are perfectly married. The architect behind this, Kyle McLean-Smith, essentially took those nouns and verbs we talked about and forced them into full sentences. He built a unified kernel where the retrieval path and the execution path are identical. Drawing from his background in copyright law, Smith noticed that music licensing agreements are basically structured hierarchies, exactly like database schemas. By using JavaScript for both the stored data and the executable logic, SeedTreeDB allows applications to evolve dynamically right inside the database kernel itself. The script is the data is the script. And that impedance mismatch, it is entirely eradicated because there's literally no boundary left to cross. The time and system overhead this saves is staggering. Let's dive into Section 5, the echoes of mumps. To really understand just how radical and yet completely proven this convergence is, we literally have to rewind 50 years. Because while HSDB uses modern JavaScript and fractal math, the core idea of natively integrating a database in a programming language isn't actually new. Let's look at the 1966 MUMPS architecture. This was a hospital system that beat modern NoSQL to the punch by 4 whole decades. Created at Massachusetts General Hospital, MUMPS was born out of a desperate need for doctors and nurses to simultaneously access real-time patient data on incredibly limited hardware. MUMPS actually proved that tightly coupling your database and your programming language works brilliantly at scale. In fact, it's still processing millions of patient records today. On a machine with just 8 kilobytes of memory, which is wild to think about today, they created globals, which were hierarchical, sparse arrays stored persistently on disk. There was 0 explicit tables or schemas. Nodes were just created on assignment, exactly like modern schema-free documents. Because the language and the database were completely unified, there was absolutely no translation overhead. The system is so blindingly fast and effective that the U.S. Department of Veterans Affairs still relies on a descendant of MUMPS today to manage records for over 9 million veterans. Finally, Section 6, comparing the 3 paradigms. So let's bring this all together and contrast these totally divergent philosophies. You basically have 3 choices: decouple entirely like serverless, meet in the middle with NoSQL, or completely converge like HSDB. Look at the compute and state coupling here. Serverless forces you to push all your state externally, focusing purely on ephemeral compute. It's super scalable, but honestly pretty complex to orchestrate. NoSQL keeps the database daemon running continuously, but expects your application logic to live somewhere else, so you're still writing drivers and APIs. Then you have HSDB, echoing the brilliant legacy of MUMPS. It pulls everything into a single, persistent, homogeneous kernel where the execution lifecycle actually retains the database structure natively. No drivers, no cold starts, just data and logic acting as one. Which leaves us with one incredibly profound question to chew on. As we keep pushing the boundaries of the cloud, will we continue to separate our code from our data? Or is total convergence the inevitable future? I mean, as serverless complexities grow around cold starts and observability, and as NoSQL requires heavier and heavier network drivers to manage distributed states, the patented architectural convergence of HSDB presents a seriously compelling alternative. It reminds us that sometimes the most disruptive innovation is simply realizing that the boundary we've been fighting so hard to cross, well, it might not need to exist at all.